Let's start with the fundamental theorem of algebra. We've already explored this, and so now it's time to finalize the definition of it. So a while ago, we did an exploration in Desmos where we explored different types of polynomial graphs. And what we were looking for at times was potentially how the degree of the polynomial related to how many zeros a polynomial would have. And hopefully you realize that the degree was the maximum amount of zeros any polynomial could have. So if we have an nth degree polynomial, function has exactly n solutions, and this is counting all the real solutions, the complex solutions, so those that might have an I in them, and any repeated solutions. Okay, so an nth degree polynomial function has exactly n solutions. So if it's a third degree polynomial function, you know that it will have 3 solutions. Now some of these solutions you might not be able to see. So we are counting all real, imaginary, and repeated solutions. So if it's an imaginary solution, you're not going to be able to see that solution, okay? If it's a repeated solution, it's going to have some special behavior, which I'm about to talk about. Okay, so let's start with our complex zeros, okay? Or thinking about imaginary. You could also call this a complex number. Probably should have done that, but okay, so if we have complex zeros, so I'm going to just kind of highlight a few things here. So anytime you have a complex zero, remember complex numbers are like that a plus bi. Okay, so any complex zeros will occur in complex conjugate pairs. Okay, so what do I mean by that? Well, for example, if we have 3 minus I is a root, then the complex conjugate, or remember, it's basically that opposite sign in the middle, so then we'll also have 3 plus I. It's also a root. So if you're given one root, that's a complex number. Remember, its conjugate is always going to also be a root. Okay? You're also going to need to deal with repeated roots. And I've been alluding to this. But repeated roots are things where we have like x squared or maybe x minus 3 cubed. Okay? So there are 2 types of these. Okay? The first one is if it is even. If we have an even repeated root, then we know that the graph will be tangent to the x-axis. Okay, so let me give you an example. So let's say I have x plus 1 squared. Okay, so x plus 1 squared, well, that's really x plus 1 times x plus 1. So I know that if I set that equal to 0, x equals negative 1 is going to be a root, right? And we'll call that a double root because of the squared. So what's going to happen here is that it's actually going to be tangent to the x-axis. So this graph, if we just think of this as a parabola, you should know where your vertex would be. It's basically going to be left 1. So at -1, which is also where my root is, right? I'm going to have this double root, which means it's not going to cross through the x-axis. It's actually going to go towards the x-axis, and then it's going to be tangent to it and back up. Okay, so you've heard the word tangent before, and maybe that came from geometry, where we dealt with circles, and then we defined like a line that was tangent by it basically touched the outside of that circle at one point. Okay, so tangent means that it's touching it at one point. It doesn't just have to be a circle and a line. So here, for example, it's the graph of this polynomial and the x-axis. So it is tangent to the x-axis. It touches it at that one root. Okay, so your point of tangency is going to be where your polynomial touches the x-axis. You could also have odd roots, or odd repeated roots, I should say. And so this is where the graph will flatten. And then it crosses the x-axis. Okay, so for example, how about I do x plus 1? But this time I'll make it a cubed root. Okay, so again, this would be like x plus 1 times x plus 1 times x plus 1. And really, I'm just getting one root out of this, right? That one root is going to be x equals -1. And I'm going to call this one a triple root, right? Because it's cubed. And so because it's cubed, I know that we're going to approach the x-axis. We're going to then flatten out and cross the x-axis. Okay, so once again, this graph here is going to go through the point -1, 0. But this time, and I'm going to try my best, it's going to come up, it's going to flatten out, touching x equals -1, and then continue up. Okay, so we call that a triple root. All right, so let's do some examples where we can apply the fundamental theorem of algebra. So example 1, we're going to find the solutions. Or solve. Okay, I'll do a couple of these. The first one, I'm going to do x cubed plus 3x squared plus 16x plus 48. Okay, so I look at this and I say to myself, well, let's see. The solutions mean all of my roots or all of my zeros. And this polynomial is raised to the third power. So at most I can have 3 roots. Now, they may be real. They may be imaginary. Okay, they could be double roots. We're not sure yet. Okay, but we're looking for all possible roots or all possible solutions. Usually I'm going to try and attempt to factor. If I can factor, that's going to be my best method. If I'm allowed to use a graphing calculator, then I can always just put this into my graphing calculator and I can find my zeros. Okay, but what if you're not allowed? So we have to have some other methods. So factoring is one method, and of course using the rational root theorem or those P's and Q's. Okay, those are always some options that are available to you. Well, I'm looking at this, it has 4 terms. And maybe I'm going to be able to factor it. So I'm going to always go ahead and try to factor. So 4 terms, I'm thinking factoring by grouping. So I see in my first 2 terms I have a common factor of x squared, which leaves me with the x plus 3. And in my second 2 terms, it looks like I have a common factor of 16. So I'm going to plot a positive 16, and I'm left with x plus 3 again, which worked out actually really nicely. So x plus 3 is now the greatest common factor that I pull out. And I'm left with x squared plus 16. Okay, so I want my solution, so I better set each of these factors equal to 0. All right, so solving the first one, well, that one's easy. That's going to be x equals -3. This one, I can't factor that anymore, but notice I just have a binomial and there's no middle term. There's no x. So I can just subtract the 16 from both sides, and then I can take the square root. So I'm going to get positive or negative square root of negative 16. All right, well, negative 16 has an I in it, right? So if I'm going to take the square root of that negative, I'm going to need an I. So this will be positive or negative 4I. So how many solutions do I really have here? Well, I have one real solution, which is negative 3. So when you graph this, you would actually see that the graph will cross the x-axis at x equals negative 3. But there will also be two imaginary solutions, positive and negative 4i. Okay, those don't get graphed on the real coordinate plane, so we don't actually see these. All right, let's try another one. Given f of x equals x to the fourth plus 6x cubed plus 12x squared plus 8x. So always, always, always looking to my first friend and asking, hey, first friend, can you help me out? And in fact, I believe that our first friend can. So I'm solving this, so I'm going to set my output to 0. I'm going to pull out an x, and I'll be left with x cubed plus 6x squared plus 12x plus 8. Okay, so from here, let's see. Can I pull out a greatest common factor in both of these and end up with the same term? So when I'm looking at this, if I pull out an x squared here, I'm going to be left with x plus 6. And if I pull out, what do they have in common? A 4. I'm going to be left with 3x plus 2. So there's no way that I can do any factoring by grouping here. Okay? However, I do know one of my roots right away, x. I can set that equal to 0. So right away, I got one of my solutions. But now this next quadrinomial right there, I need to figure out a way to solve that. And again, graphing calculator is a great way, but what if you can't use your graphing calculator? So this is where we would come to our p's and our q's. So I'm going to start out by finding factors of p, which is 8, positive and negative 1, positive and negative 2, positive and negative 4, and positive and negative 8. And I'm also going to look for factors of q, which is just 1, right? So positive and negative 1. So my p over q, or all my possible rational roots, are basically going to be all of those p's. Okay. So now I'm going to test these. Okay? So I'm going to start with, starting with 1, do my synthetic division. Let's see, am I missing anything? I don't have any terms missing, so it's going to be 1, 6, 12, and 8. So pull down a 1. Well, I'm not going to end up getting a 0 there. So I know that 1 is definitely not a root. Okay, what else can I try? How about negative 1? Nope, pretty close, but negative 1 also didn't work. Okay? Guess what? 2 also doesn't work. So I'm going to go ahead and skip to one that does work. How about negative 2? And sometimes this can be tedious. And there we go. So I finally got my remainder of 0, which tells me that x equals negative 2 is another root. Okay, and what am I left with here? Well, that's my constant, my linear, my quadratic. So I've got x squared plus 4x plus 4. And from here, I'm going to factor it because I think that's the easiest way to go. Could you have continued on with this? Yeah, with your p's and q's, checking more factors. But I think that this is going to be the easiest way to go because look at what's about to happen. Factors of 4 that'll give me 4 are 2 and 2. Okay, So that tells me basically this is really x plus 2 squared, right? So I have a double root here of x equals -2, a double root, but really I had another x equals -2. So I have a triple root of x equals -2. So we're going to say x equals -2 is a triple root. So that tells me that if I was to graph this, it would really flatten out right around, or right at -2, and then it'll cross the x-axis. So let's look at this completely. Looking at this, I've got x to the 4th power, okay, and my coefficient is positive. So what's my end behavior going to look like on this if I want to graph it? Yes, my end behavior is going to go up on both sides. Okay, and if you still are shaky on that, you want to research that. So I know that I have end behavior going up on both sides. I have one root at x equals 0 and a triple root at x equals -2. So let's just draw a rough graph of this. So again, I know I'm going to have a root at x equals 0. I'm also going to have a root at -2. And my end behavior is up on both sides. Okay, so if this -2 is a triple root, then, and I'll do my best here, as I come down, it'll flatten out and then continue through. And then at some point, oh, that does not look good. Let me try that one more time. This is very challenging for me. That's a little bit better. At some point, it's going to turn back around. It's going to come through and give us a rough idea of what our graph looks like. Now, of course, I should probably plug in -1 to see, what the value is at -1, and I should probably plug in a few more points around here to get it more accurate. But this just gives you an idea of how we're actually using that fundamental theorem of algebra, using the fact that we understand what the end behavior looks like, okay, and using the fact that we understand what our different roots look like. Okay, example 2. We are going to write a polynomial function of least degree that has real coefficients the given zeros and a leading coefficient of 1. Okay, so the first one is going to have 3, 0, and -2. So that tells me that my roots are x equals 3, x equals 0, and x equals -2. So now I want to write this in factored form, and then I can multiply it all through to get my actual polynomial. So if x equals 3, then what is that written as a factor? Well, that's going to be x minus 3, right? Because you're trying to get it back set equal to 0. So that's it in factored form. Okay? This is already in factored form. That's just going to be an x. And x minus 2, or x equals -2, will add 2 to both sides, and you know that your other factor is going to be x plus 2. So I'll bring this factor back out here, and I'm going to call my polynomial function f of x. Okay, and so now from here, I'll go ahead and I'll distribute. Now, it doesn't matter the order that you go in. You can start with, right, multiplication is not, order doesn't matter, it's commutative. So you can start by distributing this x to the first binomial, and then taking this binomial and distributing it to the second binomial. So that's one way. Otherwise, you could do the first two binomials first and then distribute the x. So this gives me x squared minus 3x. And now I need to distribute one more time. So I'm going to have x cubed plus 2x, 2x squared, minus 3x squared, minus 6x. So altogether, I'm ending up with x cubed minus x squared minus 6x. That's going to be my polynomial. Let's see, it's got the least degree possible, x cubed. It's got a leading coefficient of 1. And it's got real coefficients. So every single coefficient is a real number. So that would be my final polynomial. Let's do one more of those. This will be number 46 on page 370. So you are given -2, -2, 3, and -4i. Okay, so first of all, you have two roots that are exactly the same. So you have x minus 2, but x equals -2, but that's a double root, right? So then if I wanted to write that as a factor, it would really be x plus 2 squared. Okay, because that's a double root, right? So x plus 2. Then I've also got the factor, or the solution, that x equals 3. So written as a factor, that's going to be x minus 3, right? Because if I have x equals 3, got to get it back on the same side as x, set it equal to 0, so that's x minus 3. Okay, and then I have another solution here, which is an imaginary one, -4i. Okay, so as a factor, again, this will be x plus 4i. But let me remind you of the fact that anytime you have a complex 0, they need to occur in complex conjugate pairs, right? So if one of them had a symbol or a sign in between that was negative, the conjugate would be positive. So here I've got x equals -4i, so what else is a root? So because x equals -4i is a root, its conjugate, or with the opposite sign, 4i will also be a root, which makes that factor x minus 4i. This is really going to expand, so I'm going to start bringing my work over here. Okay, so I'm going to have f of x. All right, so first thing I'll do is I'll multiply. I have basically the square of a binomial. So there's a shortcut to that, right? We learned it. You're going to square the first term. You're going to multiply the two terms and then double them. So multiply them gives me 2x, then double it gives me 4x. And then my last terms get squared as well. Okay, I'm going to leave the x minus 3 for now. And I'm going to multiply now the x plus 4i and the x minus 4i. If you notice, that's a sum and a difference pattern. So those inners and those outers are going to cancel out, right? So all I'm going to be left with is my first terms and my last terms. So when I do that, I'm going to have x squared and then minus 16i squared. Okay, so x squared minus 16i squared. Well, this I squared really becomes like a -1. So this really is like x squared plus 16. Okay, so I'm going to put that one first. X squared plus 16. Then I've got that x minus 3. Then I've got my trinomial, x squared plus 4x plus 4. Okay, now I've got some more distributing to do, and I'm going to multiply these two binomials first. So just using my FOIL gives me x cubed minus 3x squared plus 16x minus 48. Okay, and then this is already multiplied out. So I'll continue simplifying here. So let's see, taking this and, oh, I guess there's no simplifying that can be done. So I guess it's time to just go ahead and distribute. So let's see, x cubed times x to the squared is going to be x to the 5th. X cubed times 4x is going to be positive 4x to the 4th. X cubed times 4 is going to be positive 4x cubed. Negative 3x squared now, I'm distributing that, so negative 3x squared times x squared gives me negative 3x to the 4th. Negative 3x squared times 4x gives me negative 12x cubed. Negative 3x squared times 4 gives me a negative 12x squared. Okay, now using the 16x, so distributing that, I'm going to get positive 16x cubed, then a positive 64x squared, then a positive 64x, and no matter how much room I leave myself, I'm always going to run out of room. So when I distribute this last term, I'm going to need to distribute it and just kind of write it down here. So I'm going to have a negative 48x squared. Let's see, 48 times 4, 192. So that's going to be negative 192x and negative 192. Okay, so simplifying now, going through and combining all my like terms. I don't think I have any other x to the 5th. Okay, let's see. Do I have any other x to the 4th? I do. So it looks like this one and this one. And I'm going to end up with a positive x to the 4th. Okay, let's deal with our x cubes now. So I think I just have these three. So 4 minus 12 is negative 8. Plus 16 would be positive 8x cubed. Okay, let's see. Now going down to my x squareds. All right, so it looks like I have a negative 12 and a negative 48. So I'm going to combine that to get negative 60. And then if I add 64x squared to that, that's going to give me a positive 4x squared. Okay, let's see. Now I'm down to the x's. So I've got this x and that x. So to go from 64 to 100 is 36 and another 92. 128, and it's going to be negative and minus 192. And there's my polynomial.